So the star of today's lesson is going to be factorials. As we've seen in working through these mathematical induction proofs, successfully finishing the proofs really hinges on our ability to sort of manipulate algebraic expressions in our inductive step. And one of the more complicated types of expression to understand and manipulate are factorials. They're really neat things, but they can be kind of tough to work with. So in this lesson, we're going to review how to work with factorials and how this skill will help us with some of our induction proofs. Before we get started, let's go ahead and take a deep breath. And let's begin. So this slide is probably not necessary, but I really want to make sure we're all on the same page here. So first I want us to recall what a factorial is. Okay, so we denote it with an exclamation mark. So for example, 6 factorial. 6 factorial is the product of the given integer 6 and all of the positive integers that are less than it, right? So as an example, if I asked you to write out and find an expression for the value of these factorials, 6 factorial would mean 6 times 5 times 4 times 3 times 2 times 1. And if we multiply all that out, we'll find out that this is 720. Okay? If I asked you to write an expression for 8 factorial, we'd recognize that this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if we wanted to figure out what this is, we could actually go, well, this right here is actually 6 factorial. That would be 720. And then we would have times the 8 times 7, that's 56. And so multiplying those two things together, I'm pretty sure this is 40,320. I'll double check that in a moment. But what I really wanted to get at here is just the idea that, yay, like these things can have numbers, but these numbers get big really fast. And so oftentimes we want to be able to think about these in terms of their expansions, or we want to just be able to leave them in their unexpanded forms. And a lot of this lesson today is going to be about how can we simplify, how can we sort of algebraically work with these factorials. So eventually we're going to need to be able to work with some variable factorial expressions. In other words, we're going to want to be able to deal with things like k factorial or k plus 1 factorial or even 2k factorial. But before we get there, I want to spend a little bit more time working with numbers because numbers are something that we can actually kind of see and work with and think about a little bit. So for each of these 6 expressions, I want us to sort of think about how we could simplify each of them. And I would highly encourage you guys to sort of do these one at a time and sort of check back in with me in terms of the way that I decided to simplify it. So by the way, I'm going to do this one first, and then this one, and then 3 and 4 and 5 and 6. So I'd recommend you sort of pause and unpause the video like 6 times here to go through and look at each one of these. By the way, for none of these am I actually going to compute the factorial. So all of these I'm going to really just be doing as simplifying, right? So for instance, in this first one, and this is one of the most important things for us to think about, 6 factorial is basically 6 times 5 factorial. And I kind of alluded to that in the previous kind of example that we did with the 8 factorial, right? I indicated that 8 factorial was basically 8 times 7 times 6, 5, 4, 3, 2, 1, so times 6 factorial. So for this problem here, I could write 6 factorial as 6 times 5 factorial, and then minus 5 factorial. But now that I've done that, 5 factorial is just a number, which means I could factor out that 5 factorial, and if I factored that out, what would be left? Wouldn't I just have the 6 from here, and then the 1 from the fact that this was just 1 5 factorial? So this ends up being 5 factorial times 5. And I can't really simplify any further than that. I'm just going to stop there and write it like that. This kind of simplification and ability to work with things algebraically is sort of the skill that we need in order to be able to do some of these inductions and proofs, and even some of the later like calculus, like Maclaurin series, Taylor series. A lot of them have these factorials. So these are important skills for us to work on. So I'm going to go on over and look at this one next. So if you haven't already done so, pause the video and think about how you might rewrite that. So 7 factorial times 8 times 9 times 10, this is really just the same thing as 10 factorial. 10 factorial asks me to do 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1. 7 factorial has all that stuff built into it, and so it's there, right? What about the next one, right? What about this 20 factorial over 19 factorial, right? Well, long story short, this is just going to be 20. And if you need to see why, think about expanding this, but don't do the whole thing because that would take a long time. 20 factorial would mean 20 times 19 times 18 times 17, blah, 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 all the way down to 1. 19 factorial would be 19, 18, 17, blah, 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 all the way down to 1. Do you see how the 19, 18, 17, everything else all the way down to 1 cancels, and all that's left is the 20? Okay, so again, pause the video, take a look at this next one. So what could I do over here? Well, I mean, essentially, these things both have a 9 factorial in them. I could think about this as being 10 times 9 factorial plus 9 factorial. I could factor out that 9 factorial, and that would leave me with 10 plus 1. And so that would be 11 times 9 factorial, right? And so there it is, right? Like I'm finding ways to rewrite these things. If I really wanted to, I suppose I could even make this like 11 factorial over 10. That's just occurred to me now. I wouldn't expect you to have sort of seen that. But if you think about it, this thing right here is like 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's like 11 factorial that somebody canceled the 10 out of. You might end up in an induction problem at some point where this kind of thinking is sort of the thing that you need. So it was the thing I wanted to sort of bring up. This next one here is sort of weird. I'd encourage you to sort of think about maybe rearranging, reordering these things and thinking about how you might bring these things together, and then we'll go through this one. So for this one here, I'm thinking I want to deal with the factorials. So I want to bring those next to one another. I'm going to make the 5 factorial 5 times 4 factorial. And then I've got this minus 3 times 4 factorial. And then I've got this minus 6 that I'm just going to kind of move to the end because I want to deal with the non-factorials at the end. But now these guys both have a 4 factorial. I can pull that out, and that would leave me with 5 minus 3 minus 6. So I've got 2 times 4 factorial minus 6. I could stop there. That might be good enough. If I really, really, really wanted to do more than this, I suppose I could recognize that 6 factorial is actually, I'm sorry, not 6 factorial, but 6 is actually 3 factorial. So if I wanted to, I could do that. And then over here, I could pull the 4 off of the 4 factorial to get this. Hopefully you're sort of seeing how this 4 factorial turned into this. At this point, both of these things have a 3 factorial. So I could pull out the 3 factorial and be left with 2 times 4, that's 8, minus 1. So 7 times 3 factorial. Now, you might kind of be wondering, like, what? How am I supposed to know that I'm supposed to get here? The important part is you're not supposed to get here. It's just that you can get to any step in the middle of this process. Any one of these might be useful. And so the skill that we're really working on here is what can we do? What are we allowed to do? What sorts of manipulations can be done? This last example over here, this final one that I have, the 10 factorial over 8 factorial, this one is very similar to this one, right? The difference is this is going to cancel out the 8, 7, 6, 5, 4, 3, 2, 1, right? So all that will be left is the 10 times the 9, which is 90. So these are the kinds of manipulations that we can do with numbers. Now I want to take this and spend a little bit of time thinking about how all of this sort of plays with variables. Right, so take a breath again, and we're gonna slowly move into how we work with these things with variable expressions. We got this. Now again, I want to point out this idea of variable factorial expressions is going to end up being really, really valuable as we move further into this class. It's not everywhere, but it does show up in a number of places, and so I did want to sort of pause our induction lessons and make sure we've got a sense for this. So I'm going to lead us through a few questions here. My first question, what does k factorial mean? And I would really encourage you, like, don't just listen to my answer. Like, pause the video, think for a moment, like, what would k factorial mean? Imagine that k is some whole number. What would k factorial mean, and how would you express it? How would you expand that? So hopefully you've thought of this on your own, and hopefully you're thinking, well, k factorial would mean I would multiply k by the thing that's 1 less than k. That's like k minus 1. Times the thing that's 1 less than that. That would be like k minus 2. Times the thing that's 1 less than that. That would be like k minus 3. And I would just keep doing that until I got down to 3 times 2 times 1. And that would be it. This would be k factorial. Okay? If that doesn't make sense, like pause the video and look at that again. If you look at it again and it doesn't make sense, like, join the class and ask me about it. Send me a message about it. Like, I really, really, really want to make sure that we're making sense of these things. If you've got a bit of a sense for that, let's think about this next thing though. I now want us to write down expressions for the numbers that are exactly one more than and one less than k. And let's actually pause it there for a moment. So what is the expression for the number that's exactly one more than k? Wouldn't that be k plus 1? And if you're thinking about the number that's exactly one less than k, wouldn't that be k minus 1? Now, what I'm asking us to do is I'm asking us to express and expand these, I should have had the word as in here, expand these as factorials. So if you had k plus 1 factorial, how would you expand that? What would that mean? And if you had k minus 1 factorial, what would that mean? Right? Well, k plus 1 factorial would mean you'd start with k plus 1, then you'd go to k, then you'd go to k minus 1, and so on all the way down to 3, 2, 1. K minus 1 factorial would mean you'd start at k minus 1, you'd go 1 less than that, k minus 2, then you go k minus 3, and you'd keep doing that down to 3, 2, 1. Okay, so being able to see what these things are is really valuable, because now I want to go on and use this for a real example. Imagine if I asked you to simplify something like k factorial over k minus 1 factorial. If you had one factorial variable divided by another factorial variable, like, are we supposed to distribute this factorial in and then cancel? Quick answer, no. In fact, quick point, you cannot just distribute a factorial. These are different things, but they have a lot of similarity. So I'd encourage you to sort of think about what we said up here about k plus 1 factorial and about k factorial and about k minus 1 factorial. Think about those things and think about how you might simplify this. I'm hoping that you paused the video, that you gave yourself a chance to try this. So if I actually did this, wouldn't the top just be k times k minus 1 times k minus 2, blah, 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 all the way down to 2, 1? And then wouldn't the bottom be k minus 1 and 1 less than that and 1 less than that and 1 less than, like, all the way down? Do you see how all of this stuff just cancels out and leaves me with just k? If you need to, like, pause the video, make sure that makes sense to you. And if you've got a good sense for that, then go on and think about this one. It's also going to be similar and easy if you got this one, but I want everybody to have a chance to think about it. If I have k plus 1 factorial over k factorial, how would that simplify? Right? Wouldn't this basically turn into k plus 1 times the rest of k factorial and then divided by k factorial, which means these would drop out and I would just be left with k plus 1. Okay. Now, these are fairly simple examples of variable factorial expressions. In the next part of this video, I'm going to talk about some examples that might be a little bit more complicated, that are going to sort of tie together the examples we just did here with the few that we did on the previous page, and then we're finally going to sort of end with a mathematical induction example. I've mentioned it previously in this lesson, but I think there's a lot of value in you guys practicing and trying these on your own. So for each of these 4 things, I would really encourage you to pause the video, try them on your own, and then come in and see what I decide to do with it. I smashed all these examples together because they really shouldn't take up a lot of space. These should be things that you can pull together fairly quickly. So for this first one, it's to simplify the expression k plus 1 factorial minus k factorial. So I hope that you recognize that this first thing, I could basically write this as k plus 1 times all the stuff less than that, which means k factorial, minus k factorial. And then these two terms both have a factor of k factorial. So if I factor out that k factorial, I'm left with the k plus 1 from here and minus the 1 from here. So this is going to be k factorial times k. And that's it. Like, yay, we found a way to take this thing, which was 2 separate expressions, and we basically factored it to turn it into this. Now for the next example, I want us to think about how to simplify this one. So, even if you didn't do the first one on your own and try that one, think about trying this one. If I have k plus 1 factorial, that's all the stuff, all the integers k plus 1 and lower, multiplied by the next thing above that, isn't that just k plus 2 factorial? Right? And that's it. Like we don't even need to show any work on this one. Like this is what this is. If either of those previous examples didn't make sense to you, I really, really would encourage you, pause the video, like write it down on a separate sheet of paper, sort of like think about it and process it and make sure that you can get those to make sense. And if not, like ask about them. For this next one, simplify the expression k plus 3 factorial over k plus 1 factorial. So, well, k plus 3 factorial would be k plus 3 times k plus 2 times, and then from there it would just be k plus 1 and all of the other integers smaller than that. On the bottom, I'm just going to leave this as k plus 1 factorial because I can see that these are both the same factor. And so all that's left here is k plus 3 times k plus 2. Now at this point, some of you may be wondering, like, should I FOIL that out? Should I multiply these? Should I get k squared plus 5k plus 6? And the answer is, I don't know. Like, what problem are you working on? For this problem, I would accept either one of these. But if you were in the middle of an induction proof, you would need to decide for yourself, is this enough, or do I need to go to this? We're getting to the point in math where there are right and wrong answers, but when you're working through a proof, when you're working through the steps, it's up to you to figure out whether you need to do more, whether it helps you to do more or not. So let's look at, I've just got this one last example of simplifying some of these variable factorial expressions. So we'll go through that one, and then we'll really get a chance to put some of this stuff into practice. So again, I'm hoping that you'll give yourself a chance to try this one on your own. I noticed that both of these things happen to have a factor of k plus 1 factorial. So I'm going to factor out that k plus 1 factorial. When I do that, what I'm left with is k plus 2. The k from here and the 2 from here. But hopefully you notice, hey, wait a minute. Isn't k plus 2 just the next thing in line after k? Isn't k plus 2 just 1 bigger than k plus 1? So how could I put this factorial together with this? Couldn't I together express these as k plus 2 factorial? Like, this factorial perfectly lines up with this number to allow us to write it all as 1 factorial. And hopefully you see how this kind of simplification and this kind of work could really help us to get some neat expressions for things that we might be able to really simplify well in the middle of an induction proof or something else that we might be doing. If any of these examples that I just went through were unclear to you, or if you have questions about them, please ask me, ask a friend, like reach out to someone, because the deeper understanding we have of this sort of basic work, the more fluently we can work through more complicated problems. So I finally want to sort of put some of that knowledge that we just figured out, put some of it to use in this induction problem. Use mathematical induction to prove that 2n factorial is divisible by 2 to the n for n greater than or equal to, well, let's say 0. Right? So let's start with step 1. Right? Step 1 is when I'm supposed to write this thing mathematically. Right? I want to prove that 2n factorial is equal to 2 to the n times some integer. Right? We talked about the fact that with divisibility proofs, we really want to make sure that that the thing that we have is effectively a multiple of the thing that we want to show that it's divisible by. Okay, so that's step 1. Step 2 is our base case. All right, so step 2, our base case, we want to prove true for my starting value, for n equals 0. Okay, so when n is 0, the left-hand side is going to give me 0 factorial, which is 1, and the right-hand side is going to give me 2 to the 0, right, which is 1, times some integer, so 1 times some integer. So my question is 1 equal to 1 times some integer? Yes, for m being 1. right? It's really important for you guys to know this base case here doesn't mean that the m has to be the 0 that we used. This is a different variable than the n, the 0 that we used. This just needs to be that 1 is equal to 1 times some integer. So yay, we showed that this was true for our base case, and we're ready to move on. So next we move on to step 3, which is our inductive hypothesis. Right? So step 3, our inductive hypothesis. This is where I assume that it's true for n equals k. So I'm going to assume that 2k factorial is equal to 2 to the k power times some m. Right? I don't know which one, but I'm assuming that 2k factorial is in fact going to be some multiple of 2 to the k. For the purposes of my induction proof, I'm going to assume this. And that's all we have to do for step 3. Step 4 now. Step 4 is our inductive step. And this is where I want to show that it's true for n equals k plus 1. So now I need to take the thing that I wrote up here, and I need to plug in a k plus 1 wherever there's a k. And there's a really important thing that happens right here. I've noticed in your work, some of you have been doing this and some of you have been missing it. So there's a really, really important thing here that I want everybody to catch. When you plug that k in, it has to be plugged in parentheses. So that k plus 1, it goes exactly where the k was. And so if it's right next to a 2, it needs to get multiplied by that 2. Right? So I want to show that this is equal to 2 to the k plus 1 times some p, some other integer p. Okay? So now if I simplify the inside of this thing, this will be 2k plus 2 factorial equals, well, actually I don't want to write equals because my goal is basically to make it look like this. And remember that when we do this, we recognize I have to use this somewhere. Somehow that's got to show up. So this is the point in this problem where I start wishing, like, man, I really wish this problem had a 2k factorial in it. Like, oh gosh, if only there was some way that I could get 2k factorial to show up here. How could I get 2k factorial to show up, given that what I have is 2k plus 2 factorial? Well, hopefully you remember from some of the previous practice we did in this lesson, I could make this 2k plus 2 times 2k plus 1, that's 1 less than that, and then at that point it would be 2k and everything less than that, right? But yay, wonderful. This 2k factorial is literally exactly what I wanted. Now I can replace this 2k factorial with my 2 to the k times m from up here, right? And now I'm so close. I'm just missing, it needs to be 2 to the k plus 1. So if only there was some way I could get like one more factor of 2 out of this thing. And I can, because this right here also has a factor of 2. I could pull a 2 out of this and leave me with k plus 1. And then this would be 2k plus 1. And then I'd have 2 to the k times m. These two things can be put together. I can add together their exponents. This would be 2 to the k plus 1 times k plus 1, 2k plus 1, m. And so this whole thing right here, this is that p integer, right? This thing is an integer, right? And so I hope that makes sense. If you've been making sense of these induction problems so far, then at this point you should recognize, oh yeah, sure enough, this is 2 to the k plus 1 times some really complicated looking integer, right? And so at this point, we really just need to move on and write our conclusion, right? Remember that step 5 was our conclusion. And most of you have really picked up that our conclusion is pretty much always the same. In our conclusion, we always make reference to our base case. In this case, we started it at n equals 0, and we mentioned that we showed that it was true for n equals k. It'll also be true for n equals k plus 1. And so by the principle of mathematical induction, it's true for all integers n greater than or equal to 0. So I hope that this review / extension of our knowledge of factorials was helpful to you guys, and that at this point you might have an easier time working through some induction problems and even some of the later math that we're going to do in this class that involves factorials. As always, if you have any questions, please reach out and let me help, and I wish you best of luck as you work through the practice and your continued mathematical studies.